Single photon emission computed tomography, or SPECT, is one of the most popular medical imaging modalities. Over 18 million scans are completed annually in the US, with applications ranging from cardiac perfusion imaging, bone scans, and dosimetry estimation in nuclear medicine. In a SPECT scan, a patient is injected with a radioactive biomolecule that binds to a certain region of the body, such as a tumor. The radioactive molecule emits high-energy photons which travel outside the patient's body and get detected via a gamma camera. These cameras use a lead collimator design to ensure that photons are only detected if they travel perpendicular to the camera. The SIMIND Monte Carlo program provides a comprehensive digital simulation of many SPECT scanners. Use of simulations can provide researchers essential information before conducting an actual experiment with a real-life SPECT scanner, which can be really time-consuming. In this short series of tutorial videos, I will show how to use the SIMIND Monte Carlo program to simulate SPECT. Finally, I'll show how to both open and analyze the data using the Python library PyTomography. So the main website for downloading and installing and getting access to the documentation as well is right here. I'll put a link in the video to that as well. The main thing to notice is that on the menu you have the manual as a PDF. This is going to be really important when you're using SIMIND to refer to this manual, though it may not make sense when you first start using SIMIND. But we'll go to an installation of SIMIND and you see that there are different downloads depending on your operating system, and then slightly different installation procedures depending on whether you're on Mac or Linux or Windows. But the installation is pretty basic. I'm not going to go over it here. The main thing is that you'll choose a folder where you put SIMIND on your computer. So what I've done here in Virtual Code is I've added the folder where I've installed SIMIND, and I can basically add folders to my workspace by going add folder to workspace, and I've installed SIMIND right here, so all the code is there. I've also added this SIMIND tutorials video folder, so I'm going to go through all the tutorials from scratch and move files over and things like that here, and then this other file is basically all the code completed, which I've done beforehand, but I'm going to sort of do it all with you guys as well throughout these tutorials. So the first thing we should talk about is how SIMIND is set up. There's really sort of two main commands you'll be using. There's the SIMIND command to actually run simulations, and the change command to change parameters of the simulation. Of course, we're simulating a real system. There are lots of parameters that you can change in a SPECT system, so they've sort of developed their own command just for changing parameters and configuring to specific systems. But anyways, let's start by going to the SIMIND folder and just taking a look at the structure here. So there's a number of executables that are obviously used in the SIMIND sort of source code. There's a tutorial folder with some simple tutorials that are gone through in the manual, though they're not super in-depth. And then there's this SimSET directory, which contains a ton of data files for different isotopes and different materials when you're actually running the SPECT simulation. Now what we're going to do is we're going to grab a file from the tutorial folder. So you'll have this tutorial folder that's installed, and for now we're just going to grab this point.smc file. So we'll copy this and we'll just put this in the same folder that we're in here. So I'll paste this here and I have my point.smc file. So you can see it contains a bunch of data and a bunch of simulation flags. So you'll notice that we're in the same folder as this point.smc. I can edit so by the way, the SMC file contains all the parameters for the simulation, or some of the parameters. It's really the detector parameters and certain things. There are other parameters stored elsewhere, which we'll get to, but the main parameters for now to be concerned with for simulation is contained in these .smc files. So if I want to edit the parameters of this file, I can go change point.smc, and I notice I'm in the wrong directory here, so I go to tutorial 1 and I can change point.smc, and you see that there's a sort of option menu that comes up with different numbers that you can type in. So the way it works is if I want to sort of go to option 2, I would go 2 and then enter. If I want to go to sort of menu 3, I would go 3 and enter. So there's sort of two things that you'll be interested in changing. So this is setting up the simulation. There's the general data and the simulation flags. And so again, there are a lot of parameters here. It's very easy to get overwhelmed when you start using SIMIND. For example, if I look at the general data, there are lots of things I can change for a given simulation. Things like source activity, number of projections in SPECT, pixel size and density maps. There's many different parameters here. And we don't want to go to all of them at once. They're sort of set to a default configuration right now. We'll learn more and more about these parameters as we sort of move through the tutorial series. But for now, just know that they exist. And there's also these simulation flags that exist. Again, there's 15 of them. There's less, but again, if you haven't used SIMIND before and you're not super familiar with the SPECT system, these may sort of be strange for now. So recall that in a SPECT scan, you get injected with a radioactive material. That radioactive material goes to different places in your body and emits photons. In general, of course, these radioactive materials might emit photons of many different energies, but for now, with SIMIND, if you look at the general data, we're actually set just to emit photons with a given energy of 140 keV. That's sort of the default unless you specify a given sort of molecule, but we're just stick with photons of a constant energy for now. So there's a few parameters we need to sort of go over right off the bat. So if I just go to these parameters here, you can see that the first sort of index right here is photon energy, 140 keV. If I want to change that energy, I can type 1 and then type the value that I want, for example, 120. And now you see that it updates and now it's at 120 keV. Again, if I want to change it back, I can go 1, type 140, and it's now back to 140. If I want to go to the next page, I can click enter. I can look at these parameters here, and it sort of goes all the way down to all 101 different parameters, and then it brings me back to the main menu. If I press enter, it would exit. And if I press 2, option number 2, I go back to the general data where I can edit various things. So there's two main components in every simulation in SIMIND. There's the source and the phantom. So the phantom corresponds to the attenuation coefficient everywhere in space, or the Hounsfield units. It's like a CT scan. It sort of measures the density everywhere in space, but more importantly, when you're simulating photon transport, it gives all the sort of necessary probabilities you need to actually do a Monte Carlo simulation. So the phantom sort of contains the density or attenuating properties of the material at every location in space. So you simulate a photon, it goes throughout space, and it's sort of based on the phantom here. So in real SPECT practice, this information is obtained using a CT scan, which is basically a 3D X-ray. And so the dimensions of the phantom in this case are set like this. Again, what do those dimensions mean? Well, we'll get to that in a second. And there's the actual source. So the source is different than the phantom. The source is the actual photons themselves, where they come from. It's the source of the photons. So in a real SPECT scan, this is like where the radio tracer goes throughout your body. And you can see that the source in this case is much smaller than the phantom. But again, we still don't know what these look like yet. All we know is that the source is a small little volume here. In fact, it's infinitely thin in the x-axis in this case. But the phantom is a three-dimensional object that is much, much bigger. So the phantom sort of expands. It's like a body, right? And then a small little location inside that phantom is contained with a high radioactive source. Okay, so what do these volumes actually correspond to? Well, if I look at my phantom type and my source type, index 13 and 14, you can see that they're both set to 4 here. Now, if you look at the SIMIND user's manual, and I have it on my screen here, but I'll display over top on the video, you can see that index 14 for the phantom corresponds to a horizontal cylindrical phantom, and index 15 corresponds to, as well, a horizontal cylindrical source. Now, in this case, it's sort of an infinitely thin cylinder, so it's like a line source. And then the phantom is going to be a cylinder with bigger dimensions. So you can imagine you have a cylinder of water. In this case, it's going to be a water phantom. That's set in another parameter, which we'll get to in a second. And then it's going to be a small little bit of radioactivity located in the center of that phantom. So again, you can change these parameters by playing around, but we won't do that for now. The other thing to realize, and this is sort of a strange parameter to go to right off the bat, but that's parameter number 84, which is the scoring routine. It's set to 0 right now, so the scoring routine is really the way that the data is output for you to analyze after the fact. Now 0 is what's referred to as the dummy routine. It's not particularly interesting, as you'll see when we run for a second. We're going to change this to 1 shortly. And so what 1 is going to do is it's going to give us actual SPECT projections that we can look at. So there's a number of things here. Again, enter, enter. I'll go back to general data and just look at these parameters right here. The main thing to note is that all the photons originating from the source are going to be emitted with 140 keV. Another parameter that's interesting is the number of photon histories. So this is how many histories are going to be ran. It's in units of a million, so we're going to run 5 million photons. They're going to be sampled. They're going to sort of move out. They're going to be detected by the detector, and we'll get sort of a simulated SPECT scan. So again, there's a bunch of different parameters here, so I say we just run this code. So we have a sort of parameter file here called point.smc. As soon as I exit, by the way, it also sort of generates this SIMIND.smc file. It's sort of a carbon copy of the point.smc file. This is one of the features of SIMIND. But we can just sort of ignore it. It basically gives the current state of the SMC file. There's reasons for that. But anyways, so if I want to run this code, I can go SIMIND point. So I'm using the SIMIND command for the SIMIND program, point, which refers to the point.smc file. And then I can give an additional thing if I want to, test. So this is going to, any file that's generated using this command is going to have the name test. And there's lots of files that get generated. So I can run this command. It's going to run a simulation. It's just simulating a single projection for now. So it's just one sort of photo, a projection of all the photons getting sort of hit on the camera. And it gives these results here. And there's nothing really too interesting to look at. Now the results file, it sort of duplicates a lot of stuff from the SIMIND file. And it gives some interesting sort of parameters here. Again, we'll get into these a lot more later. But you can see that we've basically ran a very simple simulation. There's not a lot of data to look at the moment, but this .result file will be important for analyzing later on. So with the dummy routine, so index 84 set to 0, we get a very simple simulation. So I'll go back, change point. We're going to set index 84 to 1. So it's at 0 right now. We'll say 84 and set it equal to 1. So now the scoring routine is 1. If you look at the SIMIND manual, that corresponds to the scatter window routine. So we'll talk about what that means in a second, why it has that name. But just know that we're doing a different routine and we're actually going to get an image now. The other thing is that we want to make sure we're not taking too many projections. The more projections you take, the longer it takes to run. So when you're doing a full simulation, yeah, you might do 64 different camera angles and store every single photo. But for now, we're going to set index 29 equal to 3. So we're just going to take 3 projections. So it means the camera, when it rotates around the patient, there's going to be 3 different projections it takes, and they're going to be equally spaced between 0 and 360. So that's what's going on. So there's going to be angle 0, angle 120, angle 240, and those are going to be the 3 different angles that the camera looks at. So there's one other thing we actually need to change as well. So I'll go change point.smc, and now I'm going to change one of these simulation flags here. And you can see that simulate a spec study is set by default to false. We want this to true. So I'm just going to say flag number 5. I type in 5, enter, and it will switch this Boolean now to true. So now it's going to simulate a spec study when we run the command. So I can exit this, and now I can run SIMIND point, and I'm going to call the file's output test. So it's going to run a scan. You can see that there are 3 different projections it needs to simulate, and it will now run for a little bit. All right, so the simulation has just completed. I'm going to clear the terminal here, and we'll talk about the files that have been output. These are the files that you'll probably be dealing with the most when you're simulating spec scans. You have the H0 files and the A0 files. So H0, okay, this is what's known as a header file. So the file format here is interfile. All the data comes with sort of this text. It's like a text file that contains all the important information about the scan, and then the actual image data, which we can't view. So this is a bit of a larger file. And you see that we have air, scatter, and total. Again, just ignore those for now. The different ones, we'll get into that a lot more later, but for now we're going to be concerned with the total file. So the total is the total number of photons that were sort of emitted and just detected by that detector. And so what we'll do is we'll open up our analysis here. And in order to open these files, I'm going to use a library, by the way, which I had a huge part in developing. In fact, I started development of this library, pi-tomography, and there's going to be a lot of videos about pi-tomography later, I promise you. And it's got a lot of functionality for various things in tomographic reconstruction. But for now, we're just going to use it for opening the SIMIND data. So for that, I'm going to import this SIMIND sort of a module from pytomography.input-output.spect. We'll also import matplotlib and PyTorch. So by the way, in order to use pi-tomography, you need to have PyTorch installed. You don't necessarily need a GPU, but you need an installation of PyTorch, and then you can install pi-tomography. Again, you can pip install it. It's very easy to do just by running pip install pi-tomography like that, and you'll get it. But I already have it installed, so I'm not going to run that. So these are the libraries that we're going to use. So we've imported pi-tomography, matplotlib, and PyTorch. So I've talked about this already in a spec simulation. There are the 2 volumes of interest. There's the radioactive source at each point in space, which is the small thing in our case, and then the attenuation coefficient. So that's the sort of CT or density everywhere in space. And so in pi-tomography, like I said, the radioactive source is the source, and the attenuation coefficient everywhere is the phantom. And the spec camera, of course, is taking pictures of the source at different angles. So the first thing we'll do is we'll actually open up these projections. So remember I said that this is the total number of photons. It's the header file. So this module we imported SIMIND, you can get the projections just by calling the get projections file with the location of the header file, and we can look at the shape of the projections. And you can see that they are 1 by 3 by 128 by 128. Okay, so where do these numbers come from? Well, this 1 on the outside, there's a reason why pi tomography has that extra batch dimension for projections, but we'll get into that later. The 3 corresponds to all 3 of the different projections. And then this 128 by 128, well, that's the dimensions of the actual photo. When you take the screenshot, you're discretizing the photons into 128 different bins in X and Y, and you're storing that as an image, like a regular image. So we can plot the projections like this, and you can see that we have this little source in the center that's creating a little image. And if I go to my different projections, well, because it's sort of isotropic, it looks the same from all these different angles from the way that the detector is rotating around it. So you can see it looks the same. Now, if we want to, we can change the source geometry so it looks different. So we're actually rotating around an object that looks different from different angles. So I'll arrange it so that I have my commands here and then my notebook for analysis on the right here. So what we're going to do is we're going to change the geometry of the source. Now, one way to do this is change point.smc. I can go to and I can modify each of these parameters individually by typing in various numbers. But there's actually another option for changing indices if you want to do it in a slightly different way. And I want to show you how to do this because we're going to do it a lot throughout this tutorial series. So one way to do it is go SIMIND point test. And so what I'm doing here is I'm putting a slash after test. And now we can specify the values of different indices. So I can either change them before the simulation, or I can change them whilst I run the simulation by putting specific values here like that. So what do I mean by that? Well, if I want to change the value of index 2, remember index 2 gave the source length. Again, that's in the SIMIND user's manual. And I'm going to set this equal to a value of 3 centimeters. And then I put a backslash. Okay, so it says that index 2, I'm giving the value of 3 to. I'm also going to change the y dimensions by going 03, and I'm going to give that a value of 4. So now we've actually modified our source distribution. Again, the files will be overwritten. They'll be called test. It's going to run the simulation again, and now these parameters are going to be modified inside the .smc file. So rather than using change, we'll set them like this. So I can run this command. It's going to run all 3 projections. Okay, so the simulation has finished. I can clear my terminal. We get the sort of same output files. They've all been overwritten. And if I open up my header file again, so now it's a new header file, and I look at the projections, sure enough, I have a source that looks slightly different. And if I change my projections, well, then I'm looking at my source object from a slightly different angle. So I have a source that's sort of a warped cylinder. You can imagine it looking like a flask or something like that. So I have my source that I'm imaging, and I'm taking photos of it from different angles. So you may have wondered where this 128 by 128 came from, and you may wonder how the spacing is defined here in this projection. Well, that's all defined in the .smc file. So again, I can change point. I don't even have to say .smc. I can change my general data, and what we can do is we can actually change the both the total length here, so the number of bins. So in this case, there's 128 bins, and the spacing. So you'll notice that I said that the thing was, I think I made it 4 and 3 centimeters. So each of the individual pixels on the detector has its own sort of resolution here. So we can change that in the simulation. So if I sort of move down here, so that information is controlled by, well, one of them is index 28. So that's the pixel size in the simulated image. Now you'll note that this is 128 by 128. If I were to just change this value, so for example, let's suppose we make it smaller. Let's change index 28 to 0.2. Again, you can do this at runtime if you want to as well. Then the pixel size is going to be smaller, but it's still going to have 128 bins. And you'll notice that it's not going to be like, you might think that it might go shifted here. It's always centered on the center. But if I have the same number of bins and a smaller pixel size, it's basically just going to zoom in like that. And so we can run the command again. So I'll just exit out of this. And I can run SIMIND point. We'll give the same dimensions as before. So I'll run the scan. Okay, so the scan is finished running. And when I open up the projection file again, you can see that it's now been zoomed in. So we still have 128 bins. We just have a smaller pixel size. Now again, if I want to change the dimensions from sort of 128 to something else, I can go change point, I can go change general data, and let's go to, I think it's stored back here. So you can see as I have my matrix size image I and matrix size image J. So this is going to be the size of the sort of I and J axes here. I can change those to be whatever I like. In this case, you know, we could change them to be, for example, something like 256. So I can go 76, 256, 77, 256. So I've now changed the image to be slightly bigger. And if I were to run the simulation again, which I will do, so I'll clear this and then go SIMIND point test, again giving the same geometry, and I open them up yet again, you can see that I now have a larger matrix size. The pixel size is constant. Because I'm having more bins here, I'm now zoomed out. So it kind of looks like it did when it started, but now there's basically higher resolution. I have more bins and I have a smaller pixel size, but the overall size is the same. So the first thing you'll notice is there's sort of strange units here in the color scale, and believe me, we'll talk a lot about what those units mean. They are extremely important. For now, ignore them. Just note that they're going to be proportional to sort of what the image looks like when you take a spec scan, but just sort of ignore these for now and know that we're going to go deep in depth in these later. Okay, so one thing you may have noticed is that there's not just the total that's output, there's also something called SCA and air. Now we won't focus so much on the air images, but the important thing is the total image and the scatter image. Now you'll recall from a spec scan that the way that the collimators are set up, when photons are emitted, it only allows photons that are traveling perpendicular to the head of the scanner, so they have to be coming in like this to be detected. If a photon comes in like this, or like this, of course it gets rejected. So the idea there is that if you have photons sort of at one point in space here, and the detector, they're only going to sort of hit the detector right here, even though the photon is sort of emitting photons isotropically. So that any photon that gets emitted and comes like this, hitting the scanner, isn't going to be detected. Now, you might think that that's foolproof and that there's no way that photons sort of traveling anywhere else will get detected. But there's something known as scatter. So the idea is if your detector's here and you have a photon, and it emits, so you have a photon traveling maybe in this direction, but then it scatters in the phantom. So the phantom has attenuating material. The photon hits maybe a water molecule or something inside the body, and it moves in a different direction. Now, if it just so happens that a photon is emitted, and then it scatters in such a way that it travels perpendicular to the detector, you detect an event that originated here, but is measured up here, when in reality it should be measured right here. So you're sort of measuring a photon that's been detected in sort of the wrong location. So you've misrepresented the location of that photon. So this is what's known as scattered events. And so the total events, when you just take a spec scan, is going to include the ones that really are coming in like this, and then ones that occasionally sort of go in another direction and scatter and get detected. And so that's what the scatter is for. So these scatter windows, they contain only photons that have sort of scattered and then been detected. And in reality, like when you take an actual spec scan, you do not know the ones that have scattered versus the total. You only have access to the total. Now, the advantage of the Monte Carlo simulation is you can separate the scattered from the total because, of course, it's simulated, and when you track the photons, you know which scattered, but in real life, you don't have access to this scattered window. It would be very helpful if we did, but we don't. And so what we do have access to is each individually. So what we'll do is we'll open up both what we'll call the photo peak, I'll explain the naming of that later, and the scatter window. So these are only photons that have scattered. So this one contains ones that have been detected and ones that have scattered, whereas this one contains sort of things that only have scattered. And if I want only the primary events, so only the ones that travel sort of directly into the detector, well, I can subtract the scatter from the photo peak. So I can open up all these files and I can plot them, and now you can see that I have my photo peak here, I have the scatter, and then I have the primary. And I'll make this a little bit bigger to see. And I'll change the color scale here a little bit. Go 0.05. So if I plot these, you can see that the photo peak contains all these different events here, and then these are ones that have been scattered, so they've gone like this and been detected. That's why they're sort of detected outside the main volume of this flask-like thing that we're simulating. And then the primary, you can see that all the events are sort of located right near where it is. So this sort of gives the scatter and then the primary. So one of the things that people often get confused about in SIMIND that I've noticed a lot is what the units mean here when I simulate. You'll recall that if I look at my change file, So let's go change point.smc, and I go to 2, and I move to index 25. Well, that's the source activity. Sorry, I meant index 26. You can see that we've simulated 5 million photons. So that makes sense. You have 5 million photons that have been sampled from the sort of source configuration, and we're going to detect them. So you would think that the number of detections that we get should be an integer value. But in reality, there are these sort of small numbers here that not only aren't integers, but they're very, very, very small values. So what exactly do these values mean? Well, for that, we need to understand what exactly the units of these are. So in an actual spec scan, you count photons, your units are going to be counts. Now, it turns out that these units here aren't in units of counts. And you might think, why would this program do this? Why is it giving us something that isn't representative of a true spec scan? Well, there's very good reasons why they give it in the units that they do. The other thing to notice before we get into that, again, I'm sort of building this up, is that index 26 is the total number of photons that we simulate. I can change this to 50, 500, 5,000, whatever number I want here. And you'll notice if you run the simulations, I'm not going to do it right now, that these numbers don't change. So these numbers are invariant to the total number of photons that you simulate. A real spec system, like I said, has units of counts. These units here have the following units. They are counts per second per megabecquerel. You might think, what the hell? This is very confusing. What does this mean? Counts per second per megabecquerel. What does seconds and megabecquerels have anything to do with the scan? Well, they're important. Okay, there's two main reasons why that's important. When you inject a patient, you inject them with a certain activity. That's one parameter. When you take a spec scan, you collect images for a certain length of time. So that's seconds. So there's two main things there. There's the activity you inject the patient with, and there's the time per projection, right? And so if I give my units of counts per second per megabecquerel, what this allows us to do is we can take this data and we can scale it depending on the length of time of the scan. So for example, if I want to simulate a scan that each projection is measured for 15 seconds and my patient is injected with 5.5 megabecquerels, I can scale these values here by both the activity and the time, and then I get units of counts. Well, almost. We'll talk about that in a sec. But the main point is that if I want to get units of actual detected counts, I need to scale by both time. So how many ever seconds per projection? Again, 15 seconds is common for clinical scans, and then activity, well, maybe 5.5 megabecquerels. So these are units of counts per second per megabecquerel. So then if I sort of define, well, let's say I have 10 megabecquerels here. That's a little bit high, but okay, we'll go with it. And 15 seconds per projection, we'll define those times. So then I can open my photo peak. I scale by activity times time. So my units of counts per second per megabecquerel, well, I multiply by megabecquerels, I multiply by time. And now I get this scan here with values that look a little bit more appropriate. But there's still an issue. Even though I have units of counts here, it's technically units of counts, they're still not integers. And in reality, if I have a given sort of bin and I'm counting number of photons, I can only get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here I have sort of a continuous spectrum of counts. So how could I possibly have units of counts when counts are by definition discrete integers? Well, that's where we get into the statistics of the spec scan. So a little bit of an interlude. Maybe you've taken a bit of statistics. Maybe you know something about Poisson random variables. Maybe you know something about counting experiments. So whenever you sort of measure data in the field and you're doing a counting experiment, which means you count the number of things that occur within a fixed time interval, many of those are related to the Poisson distribution. So for example, if you sit by the side of the road, you stand there and you count the number of cars that drive by on the road, for example, in a 5-minute interval, and you do that many, many, many times, and you plot how many cars, you plot a histogram of the number of cars in each interval that you measure, you'll get a Poisson distribution. I mean, that's supposing that the traffic is relatively constant within the total time of your experiment. This is also true for the number of calls per hour at a call center, number of arrivals at a restaurant, etc. These things are Poisson distributed. So what is the Poisson distribution? So you can look up the Poisson distribution if you don't know it. It's got a pretty well-defined shape, but it's a discrete distribution, which means the things that you sort of measure from it, the number of cars that you count, the number of calls that you count for the restaurant, they're going to be discrete numbers. So that's what we would call G here. G is a random variable. And G is distributed according to the Poisson distribution with something called G bar. So G bar, the mean of the Poisson distribution, well, that doesn't have to be an integer, right? The mean of the Poisson distribution isn't necessarily an integer. It can be any real number. So that's something important to understand about the Poisson distribution. Your distribution is characterized by a real number, so it could be 2.578, but the actual sort of statistics that you draw from that distribution are discrete integers. So that's what a Poisson variable is. That's what you measure in a SPECT scan. So now you sort of understand what's given here, these units, they're continuous for every pixel. What they're really telling you is the mean of the Poisson distribution. So if I were to actually simulate a real scan, I would need to take each one of these pixels that I get here and draw a Poisson random variable where the mean is given by sort of the relative brightness here. That would simulate a real SPECT scan. Now, the beautiful thing about that is I can simulate multiple SPECT scans with the same set of projection data from SIMIND. So for example, here I take my activity and my time, I get the projections, and now I'm going to call torch.Poisson. What that will do is every single value in those projections, it's going to draw a Poisson random variable based on the sort of, I guess, brightness here in that image. And if I now plot this image, again, I need to fix this, then you can see that this is really what the real SPECT scan is going to look like. And so you'll notice that it is much, much noisier than what you get here from SIMIND. Now, there's a few things that I want to sort of end with before we end the first video in this tutorial series. You'll notice that this data here is a little bit noisy. And of course, when you take a SPECT scan, you expect to get noise. Another thing to make really important here is that the noise in this and the noise in this come from very different sources. The noise in this comes from drawing the Poisson random variables, which is us simulating a real counting experiment in a real SPECT scan. Now, in a really good simulation, this would be noiseless. Now, we can only simulate finitely many photons in a reasonable amount of time. What you see here is that there's still a little bit of noise because we've only simulated, like I said, finitely many photons. This noise originates from uncertainty from doing not infinite number of events in the Monte Carlo simulation. So the more photons you simulate, you'll get a smoother sort of image here. But again, like a way to misinterpret this would be to think this is representative of a real SPECT scan and this is just the noise that you get. No, that's not true. This is the noise inherent from the Monte Carlo simulation. Now, what I recommend doing after this video, you have these files here. You could change the phantom type and the source type. You can change their dimensions as we did in this video. Try simulating different things, trying simulating different projections. If you want to, you can change index 29 and simulate more projections. But it's really good to get a good feel of using the change program, changing parameters. You could even change them in the change program, or you could do it like what I did and sort of give the parameters here like that. So there's many options for getting used to running the SIMIND program. But you should now be comfortable in running very basic SIMIND simulations, changing the dimensions, changing the scaling sort of each individual pixel, and then generating data that is representative of a real scan. I hope that you enjoyed this video and it's useful, and I'll see you in the next tutorial video.